Temperature sensors give an output proportional to temperature. Most temperature sensors have a positive temperature coefficient, which means that the sensor output goes up as the temperature goes up. But some sensors have a negative temperature coefficient, which means that the output goes down as the temperature goes up. Many control systems require temperature sensors, if only to know how much to compensate other sensors that are temperature dependent. Some common types are discussed next. The bimetallic temperature sensor consists of a bimetallic strip wound into a spiral. The bimetallic strip is a laminate of two metals with different coefficients of thermal expansion. As the temperature rises, the metal on the inside expands more than the metal on the outside, and the spiral tends to straighten out. These sensors are typically used for on-off control, as in a household thermostat where a mercury switch is rocked from on to off. In the diagram shown, when the temperature increases, the tube containing liquid mercury rotates clockwise. When the tube rotates past the horizontal, the mercury runs down to the right and completes the electrical connection between the electrodes. One distinct advantage of this system is that the output from the switch can be used directly without further signal conditioning. Currently, mercury switches are being phased out because of the environmental reasons, but contact type switches are taking their place. Thermocouples. The thermocouple was developed over 100 years ago and still enjoys wide use, particularly in high temperature situations. The thermocouple is based on the Seebeck effect, a phenomenon whereby a voltage that is proportional to temperature can be produced from a circuit consisting of two dissimilar metal wires. For example, a thermocouple made from iron and constantan, an alloy, generates a voltage of approximately 35 microvolts per degree Fahrenheit. Figure A illustrates this situation. We can think of the junctions at each end of the dissimilar metal wires as producing a voltage. So the net voltage, V net, is actually the difference between the junction voltages. One junction voltage is on the probe and is called the hot junction. The other junction is kept some known reference temperature and is called the cold junction or reference junction. The output voltage from this system can be expressed as V net is equivalent to V hot minus V cold. In practice, the thermocouple wires must connect to copper wires at some point, as shown in Figure B. So there are really three junctions. However, it turns out that the total voltage from the two copper junctions will be the same as the single cold voltage, V cold, of Figure A, assuming the copper junctions are at the same temperature. So the analysis is unchanged. Traditionally, the cold junction was kept at 32 degrees Fahrenheit in an ice water bath, which is water with ice in it. Ice water was used because it is one way to produce a known temperature, and so V cold becomes a constant, leaving a direct relationship between V net and V hot, which is V hot is equal to V net plus constant. Modern systems eliminate the need for ice water. One method is to maintain the cold junction at constant temperature with a control system. This can be used if there are many thermocouples in a system that can be referenced to the same temperature. Another method used by a computer controller is to simply look up a table, the value of V cold for the ambient temperature, and add this to V net to yield V hot. Still another way to eliminate the ice water bath is to use a temperature sensitive diode in an interface circuit that makes the thermocouple output behave as if the cold junction were still at freezing, even though it's not. The diagram shows such a circuit for an iron Constantine thermocouple. The cold junctions are maintained at the same temperature as the diode by mounting them all on an isothermal block. As the ambient temperature increases, the diode forward voltage drop, about 0.6 volts, decreases at a rate of about 1.1 millivolts per degree Fahrenheit. This voltage is scaled down with R2 and R3 to 28 microvolts per degree Fahrenheit, which is the same rate that the real cold junction voltage increases with ambient temperature. By subtracting with an op-amp the effect of the ambient temperature changes on the cold junction, we get a single thermocouple voltage that is directly proportional to temperature. Commercial thermocouples. Commercial thermocouples are available with different temperature ranges and sensitivities. Sensitivity being a measure of volts per degree. The graph shows the volts versus temperature curves for the major classes of thermocouples. As you can see, type J, iron constantan, has the highest sensitivity but the lowest temperature range. Type K, which is chromel-alumel, has a higher temperature range but a lower sensitivity. And type R, platinum rhodium, has an even lower sensitivity but can work at higher temperatures. Tables are available to give precise thermocouple voltage temperature relationships for both degrees Fahrenheit and degrees Celsius. Chromel is an alloy of nickel and chrome plus 9 other elements. And alumel is an alloy containing nickel, manganese, aluminum, silicon, and 9 other elements. Thermocouples are simple and rugged but require extra electronics to deal with the inherent low sensitivity and cold junction problems. However, because they are linear over a limited range, reliable and stable, they enjoy wide use in measuring high temperatures in furnaces and ovens. A resistance temperature detector is a sensor whose resistance changes as its temperature changes. The resistance increases as the temperature of the sensor increases. A wire, such as platinum, is wrapped around a ceramic or glass rod. Sometimes the wire coil is supported between two ceramic rods. Platinum wire has a temperature coefficient of 0.0039 ohms per ohm per degree Celsius, which means that the resistance goes up 0.039 ohms for each ohm of wire for each Celsius degree of temperature rise. RTDs are available in different resistances, a common value being 100 ohms. Thus, a 100 ohm platinum RTD has a resistance of 100 ohms at 0 degrees Celsius, and it has a positive temperature coefficient of 0.39 ohms per degree Celsius. PT100 sensors are the most common type of platinum resistance thermometer. Often resistance thermometers are generally called PT100 sensors, even though in reality they may not be the PT100 type. PT refers to the sensor is made from platinum, PT, and 100 refers to the 100 ohms at 0 degrees. RTDs have the advantage of being very accurate and stable. Characteristics do not change over time. The disadvantages are low sensitivity, small change in resistance per degree, and relatively slow response time to temperature changes, and the high cost. Now go to an example using an RTD. A 100 ohm platinum RTD is used in a system. The present resistance reading is 110 ohms. Find the temperature. A solution. A reading of 110 ohms means that the resistance has gone up 10 ohms from what it would be at 0 degrees Celsius. Therefore, knowing the temperature coefficient of the RTD to be 0.39 ohms per degree Celsius, we can calculate the current temperature. 10 ohms divided by 0.39 will give you 25.6 degrees Celsius. A thermistor is a two-terminal device that changes resistance with temperature. Thermistors are made of oxide-based semiconductor materials and come in a variety of sizes and shapes. Thermistors are non-linear, therefore they are not usually used to get an accurate temperature reading, but to indicate temperature changes, for example overheating. Also, most thermistors have a negative temperature coefficient, which means the resistance decreases as temperature increases. as illustrated with the solid line in the graph of Figure A. A very desirable feature of these devices is their high sensitivity. A relatively small change in temperature can produce a large change in resistance. Figure B shows a simpletron thermistor interface circuit. By placing the thermistor in the top of a voltage divider, the resulting output voltage is relatively linear and has a positive slope, shown as a dashed line in Figure A. The resistor R value selected should be close to the nominal value of the thermistor. Thermistors come in a wide range of resistances, from a few ohms to 1 megaohm, selection of which depends on the temperature range of interest. Higher resistance models are used for higher temperatures to increase the sensitivity and to keep the sensor from drawing too much current. Consider, for example, what would happen if we used the thermistor shown in the temperature range of 150 to 200 degrees Fahrenheit. The sensitivity is only 0.1 ohm per degree Fahrenheit, and the normal resistance is very low, 15 to 20 ohms. If we were to operate the same thermistor in the 50 to 100 degree Fahrenheit temperature range, the sensitivity is much higher, 2.6 ohms per degree Fahrenheit, and the nominal resistance is higher, between 50 and 180 ohms. Integrated circuit temperature sensors. Integrated circuit temperature sensors come in various configurations. A common example is the LM34 and LM35 series. The LM34 produces an output voltage that is proportional to Fahrenheit temperature, and the LM35 produces an output that is proportional to Celsius temperature. Notice that it has three active terminals: supply voltage Vs, ground, and Vout. The output voltage of the LM35 is directly proportional to degrees Celsius. That is, Vout is equal to 10 millivolts per degree C. This equation states that for each 1 degree increase in temperature, the output voltage increases by 10 millivolts. If only positive temperatures need to be measured, then the simple circuit shown in the spec sheet can be used. If positive and negative temperatures must be measured, then the second circuit is used, which requires a positive and negative supply voltage. Let's look at an example. Construct a temperature sensor using the LM35 that has the following specifications: a range of 5 to 100 degrees C and a supply voltage of 5 volts with an output of 0.1 volts per degree C. Solution: the range requirement is no problem because the LM35 has an operating range of minus 55 to 150 degrees Celsius. The task comes down to specifying the circuit and amplifying the output to meet the specs. Because the temperature range is positive, we can use the simple circuit using plus 5 volts for the supply voltage. The specification calls for a 0.1 volt to represent 1 degree C, which is 10 times greater than the LM35 output. This requirement can be met with an op-amp. The gain of the amplifier can be set to 10 by a proper selection of resistors. The gain is RF over RA plus 1, and if we select 90 kilo ohms and 10 kilo ohms, we get a gain of 10. The LM35 is a convenient IC to work with because the output voltage is in degrees Celsius. Some ICs, such as the LM135, provide an output that is in degrees Kelvin. Another device, the AD7414 from Analog Devices, is a complete digital temperature monitoring system. In a small 6-pin IC, it has a temperature sensor, a 10-bit ADC, and a serial interface. It can also be programmed with high and low temperature limits. One of the output pins indicates when a programmed limit is exceeded. Still another device, the TMP01, also made by Analog Devices, was designed specifically to be a single-chip thermostat. 3 external resistors establish the upper and lower set points. the TMP01 outputs can directly drive relays to turn either heating or cooling on as needed. That brings us to the end of our temperature sensors.